Hello, everyone. Thank you for continuing with us in this series. So before, we had a couple of videos. One, we introduced terminology and sign convention for concave and convex mirrors. Then we did the ray tracing, and we used the thin lens equation to get the image of an object sitting outside the focal point of a concave mirror. The convex mirror will come in the next series. And then now we're going to analyze the same, but for an object inside the focal point or of a concave mirror. And when we're done with this series, before we get into convex lenses, we'll do some exercises just to basically hammer the point across. Okay, so before we begin, the usual, please like, subscribe, comment, share, and hopefully you are finding all this interesting and helpful to you. So let's begin. So again, terminology, quickly. Concave mirror. This is the dark side right here. This is the light side or the reflective side. Focal length. This is the radius of curvature. Objects here. Their distances are positive. This is D sub O. And if the image happens to be here, then D sub I is also positive. Again, this extends all the way here. But if the image is here, then D sub I is negative. Okay? So let's begin. Here's a focal length. So I have a DO to 1 to roughly 3. So say DO equals 3 something, 3 units. Then 1, 2, 3, another 6. So the focal length is at 6 units. It can be centimeters. The height is 2 centimeters or 2 units. The radius is 12 units. So ray tracing, again, a little bit different than lenses. So first ray coming in parallel to the optical axis reflects through the focal point. So here it is parallel, reflects through the focal point. Oops, maybe I should take these. Yeah, let me remove these. I'll put them on the other side in a minute. You'll see why in just a second. Okay, no big deal. Now we have a ray perpendicular to the lens, reflects on itself. So here it is, reflects on itself. And one going through the focal point reflects parallel. So one appears as if, again, appears to go through the focal point. I couldn't get it to go down exactly. It goes up parallel. Okay. So again, it's tough to do sometimes these drawings using using the computer. But these are the 3 principal rays. Now, as we can see here, that they're diverging. This is going down, that's parallel, and this one, they are not going to meet here. So they're going to meet back there. So we trace this back, the reflected ray, and we trace this back, again, the reflected part of the green, and we trace the reflected ray, then they meet over here somewhere. And there's the image. It's a virtual image. It's upright. And let's just rewrite things. So DO was 1, 2, 3 units. F 6. They're all in units. R is 12. HO was 2. Now here HI, I don't know, maybe it's 3.5. So we got H sub I to be 3.5. It's positive because it's up. And 1, 2, 3, 4, 5, 6, between 6 and 7, maybe closer to 7. So D sub I is, I guess it's going to be negative, right? Negative 7, roughly. Okay, we'll see what the lens equation gives us. That's how we do that. That's a virtual image. And this is actually, you could see that in hotel rooms. They have them in the bathroom. These mirrors that basically, it's like two mirrors. You flip it, you see one is magnifying mirror. This is it. This is a magnifying mirror. Okay. And just like a magnifying lens, you want to see the object. If you're looking at your face, you want to see it upright. You don't want to see it inverted. You want to see it magnified. Okay. So these mirrors are out there, and you can, again, buy them from a store, you know. And these are the concave mirror. But when you put your face close to it, that means the object, which is your face, is inside the focal point. And that's when you see things upright and magnified. Okay. So let's see now what the lens equation gives us. So lens equation, 1 over f, this 1 over do, this 1 over di. I want to compute di. So rearrange things. Get a common denominator here. And flip to get di. Okay. So let's see. do is 3, di is 6. So that is these, sorry, f is 6. So it's 3 for do. F is 6 over 3 minus 6. So here we have 3 times 6 over 3, negative 3. The 3's cancel out, leaves me with negative 6 units. So negative 6 units, it's virtual. So we go here, and again, we got roughly negative 7. And again, these rays are not quite the way I wanted them to be, but that gives us a good estimate that, yes, instead of it being right here, it's over there a little bit. That's fine. Okay. Okay, so this has to go down a little bit more. And again, it was very hard to get them, but we got the idea. Again, these are the 3 rays. Very, very important to draw them that way. And now magnification. Negative di over do. So negative 3 over do. Oh, negative 6, I'm sorry. Di is negative 6, and do is 3. So negative 6 over 3, which is 2. So magnification of 2. So this should measure roughly 4. This is 2. This measures 4. Yeah, we fell short a little bit. Okay. And now let's go do h sub I, which is m times h sub o, because m is h sub I over h sub o. M is 2 times h sub o, which is 2. We should see 4 units. Again, diagram is a little bit off, but that's fine. Usually these give us a rough idea where things should be. Okay. So let's review this just real quick. Again, a ray coming in parallel to the optical axis is reflected through the focal point. A ray perpendicular to the mirror reflects upon itself, and that's the ray through the center. An array parallel to the axis, going through the focal point, refracts parallel to the axis. They don't meet on this side, they meet on this side. If we extend the reflected rays back, and wherever all 3 of them meet, that is the image right there. Virtual upright. Okay. Now, I want to illustrate, I will talk a little bit about the focal point. So we have this length equation. And I want to talk when DO is less than the focal point. Okay. So if you were to find the focal point from here, just do the usual math. So let's look at the top a little bit. DO is positive, right? From right here. It's less than the focal point, but it's positive. It's on the light side of the mirror. Now, DI, if it's a virtual image, again, whenever we're in this situation, whenever DO right here is less than F, we're going to get a virtual image or a negative DI right here. Okay. So DI is negative. So the product at the top is negative. Okay, so I'm going to get a negative number. Now let's look at the denominator. Let me rearrange this. Let me rewrite the denominator like this. Now I know that DO is positive and DI is negative, but I'm adding them right here. So I'm adding a positive number with a negative number. The top has already been established to be negative because DI is negative and I'm multiplying it by a positive number. So the top is negative. So F equals some negative number here over. Now I have DO plus DI. Now DO is positive and DI is negative. So basically I'm subtracting two numbers here. Now I have to be careful because so I'm subtracting two numbers. Let's just say 3 minus 6 versus 6 minus 3. We are dealing with a concave mirror. A concave mirror has a positive F. Positive F. Since the numerator is negative, we expect the denominator to also be negative, so that when I divide two negative numbers, I get a positive for F. Which means the distance between the mirror, I'm going to do it right here. Here's the mirror. If this is the object, the absolute value of the distance, so the object is basically closer to the mirror than the image. Okay? If it's closer, then I'll get something like this. And then I'll get a negative down here. I'll get a positive up here. I mean, a negative up here. Negative over negative is positive. If the object distance is greater than the image, the virtual image distance, I'll still get a negative on top, but a positive at the bottom. Negative over a positive is going to give me a negative number, which means the focal length of a concave mirror is negative, which is a contradiction. So one thing we can learn from this, just from the math, and we're going to illustrate this with the lab a little bit later, that as I move the object inside the focal length closer to the mirror, its distance to the mirror is less than the distance of the image to the mirror. This is always closer to the mirror than the image. Okay? That's what this is saying. And that's just some good insight to know that always the object inside the focal length is closer to the mirror than its image. Okay? And that comes just from the math right here. So this does it. In the next set of videos, I'm gonna start with the lab, where we're gonna go over concave, convex mirrors, look at the different situations, just move things around just so you can see how things look. Then work out exercises, just like we did with the lens, where we'll do it using the lens equation, then we'll do it using ray tracing, and just to verify that the lens equation and the ray tracing sort of like complement each other. Okay? Thank you for your time, and I hope to see you in the next couple of videos with these labs and exercises.